Welcome again. So today we'll continue talking about continuous time signal spaces. With the P norms, where P is less than infinity. Okay, so we've covered the P equals infinity case. And so last time what we did is we showed by example that if you take the set of continuous signals with compact support on some time domain, continuous time domain T with the P norm, this is not complete. All right, and this is true for any continuous time domain T. And any P 1 to infinity. Okay, and this is different from the P equals infinity case, where in at least one case, namely the case where the time domain was compact, then this space of continuous signals with compact support was simply the space of continuous signals, that was complete with the infinity norm. Okay, so with the P norms, it's never the case, and it's really just because the P norms are integral norms, and so they just don't capture enough of the local behavior of a signal to kind of control it as much as the infinity norm does. And so, for example, one of the things that we saw in our example is the property of this space that was violated by our non-convergent Cauchy sequence was the continuity. Okay, and you know, the spaces of continuous signals with the P norm, again P less than infinity, those are not tied very tightly to the notion of continuity, like is the case for the infinity norm. So, you know, we saw with the infinity norm, for example, that all the completions, even if our space wasn't complete, the space of continuous signals with compact support wasn't complete, the completion still consisted of continuous signals. That's not going to be the case here. Okay, so let's start thinking about the question that we posed at the end of the last lecture. And that is, what is the completion of these spaces? Okay, and so now would be a good time to go back and reconvince yourself of the importance of completion, because we're going to expend a significant amount of effort to characterize the completion of this space. Okay, and it had better be worth it. And so now, as I said, is a good time to sort of think to yourself in quiet contemplation of why the notion of completeness is important, and whether that's something that you feel like you really want. Because we're going to have to introduce some heavy concepts in order to describe this completion properly. Okay. But let's do like we have done in all of the cases where we've talked about completions in the past. So in the discrete time case, and in this case with the infinity norm, what we did to arrive at completions is we guessed. Okay. And then, I didn't prove that the guesses were correct. And that's because in those cases, those proofs are not that hard. Right? Once you have the correct answer, the correct guess, then the proving that that's the completion is just a kind of rote bit of analysis, like you would do in an introductory real analysis course. Okay. But in this case, we're going to see that that's not true. But nevertheless, let's start out with a guess. All right. And our guess in this case will be motivated by what we did with the corresponding p's in the discrete time case. So in the discrete time case, let me not deal with sequences, but signals. So we're going to deal with C finite of T F with the P norm. And so the completion, I said, and motivated, and I think what I hope is a compelling way. Okay. So if you take that as your starting point, and there's not necessarily a good reason why you should, but let's just do that. Then the good guess, or at least a corresponding guess, for the completion of C0 CPT F P norm. And again, I'll stop writing this at some point because it gets dull after a while. I'm only interested in this case now. Okay, so it might be, and so the first thing we need to understand is that unlike in the p equals infinity case, when the completions were continuous, we saw by our example last time, we're going to have to abandon continuity. Okay, and so your guess is kind of going to be, and already right off the bat, you run into a problem of understanding what the symbols mean. Okay, so there's a guess for the continuous time case, which is analogous to what we did in the discrete time case. Okay, so here the little p norms were defined by summations, and here they're defined by integrals. And so it seems like a good guess for the completion is just going to be what turned out to be true here with the sum swapped for an integral. Okay, and let's call this something. let's call this capital R. And there's going to be, it's going to be funny and completely unmotivated notation for the moment, but that's okay. It's just a symbol. Okay, so let me call this collection that, okay? And as we are going to see, R is going to stand for Riemann integrable, okay? And really that just means, and then there's a P corresponding to the fact that there's a P there. And the parentheses is something we'll get into when we have a little bit more information at hand. So we're going to talk about functions f for which this thing is Riemann integrable, meaning that this integral exists and it's finite. Okay. All right. So that's our guess. So if that was correct, we would do. I would just say, well, then it's a straightforward matter to show that this is, in fact, the completion, and we would kind of move on, but it's not, of course. So there's a few problems. Sorry, let me, before I do that, maybe just to make sure so if you talk about a completion, the completion, of course, has to be normed. And of course, the norm here is going to be the P norm. Okay, so that's our completion. So it's this space with this norm. Okay, so now problems. Well, there's the problems that I'm going to present. There's others, but the problems that I'm going to present here are two. One is relatively straightforward to combat, and the other one is not. Okay, so the first one is kind of the elementary one, and that is that this is not a norm. And you may sort of want to protest at this time, because you'll remember that I spent some time when I introduced these kinds of norms back when I talked about the 12 examples of norms on 3 different kinds of vector spaces. I took some time to prove that this was a norm, but we're doing something slightly differently here. But it's different in a crucial way. When I proved that this was a norm, I did that assuming that f was continuous. Okay, so if you restrict this thing to continuous signals, then yeah, it's a norm. But we're not doing that now. Okay, and that leads to the consequence that this actually isn't a norm. And so which of the norm conditions does it violate? Well, it violates the definiteness condition. So certainly it's homogeneous and it satisfies the triangle inequality. And again, you have to do a little bit of work to prove that. And we'll look at that in the p equals 2 case a little bit later. So those two conditions are satisfied, but it's the definiteness here that is the problem. And so the problem is that there are f's that are non-zero with zero norm. Okay, and this is not exotic. So just take a signal that's 0 except at a single point. Okay. Okay, so you can and we're going to do this carefully when we actually talk about what R means, the Riemann integral. But what we'll see is that if you take a function like this that's zero except at a single point, then this norm will be zero. But the function is not the zero function. Okay, so that's one issue. Now that's a relatively mild issue compared to the second one, which we're going to say in just a second. But issue one is kind of why we're in our notation here. We're putting parentheses around that. But there's a simple way to overcome that. But now isn't the time to do that. Okay. So this is easy to bookkeep. And kind of really that's what it is you overcome that problem kind of by just naming things in the right way. Okay, the second problem is more interesting, and that is there are Cauchy sequences in RP that don't converge. Okay, and we'll kind of see a hint at this. It's not, we won't be as good about this as I would like to be, because it just takes a bit of time to do that kind of correctly. But we'll kind of see why this arises, okay? But for the purposes of our conversation right now, it's enough to notice that this immediately makes this a pretty crappy guess at a completion because it's not complete, all right? But for what we want to do right now, just suffice it to say, this is difficult to overcome. Okay, in the sense that it's not just sort of an elementary adjustment that you need to make to certain definitions. What the problem here, it turns out, is R, which refers to this integral that I'm taking here, which I'm taking to be the Riemann integral, and it's a structural difficulty with the Riemann integral as it's normally known. Okay, so the difficulty has its origins in defects of the classical Riemann integral. Okay. All right. And so therefore what we're going to do is we're not going to use the classical Riemann integral. We're going to use a different notion of integral, and we're going to spend some time talking about that. All right. So it's, I think, worth maybe saying a few words about what the objective here is. Okay. We will introduce a different integral than the Riemann integral. And this is called the Lebesgue integral. Okay. And so it's, the Riemann integral has a definition, and you probably have seen at least a light form of that definition. What we want to do here is we want to first give, a relatively clear presentation of what the Riemann integral is, point out some of its problems, and then introduce a different integral that solves those problems. Okay. And so we have these two integrals, and this one is going to agree with this one in every case of interest. Okay. But the definition of this integral is going to have nice properties which will overcome this problem. Okay. And so let me just say this: the point of doing this is not to enlarge the class of integrals you can calculate. Okay. And in our introductory calculus courses, we are presented with integration, kind of as an activity. It's like gymnastics or archery. It's something you do. You do an integral. We're not interested so much here in doing integrals. We will need occasionally to do an integral, but I'm just going to assume you know how to do integrals. So all the various kinds of tricks, standard tricks that you learn in a introductory calculus course to do integrals, and I'm not going to be teaching you any more tricks like some advanced version of integration by parts or something. It's not going to be that. It's not the integral as a thing you do. It's an integral as a concept. Okay, so what is the integral? So instead, we aim to give a better definition of the integral. Okay. And better can mean lots of things, but for our purposes, it's going to mean it's going to give complete, when we use the corresponding integral in this kind of a characterization here, it's going to give a space which is actually the completion. So as I said, the R here stands for Riemann, because that's the integral that you use. Nobody uses this space, and it's exactly for that reason. But the space that we're going to talk about is going to be the space LP. Okay, and the only difference between LP and RP is the definition of the integral in there. Okay, and so these spaces we're going to come up with are going to be called the LP spaces. And you notice we use an L here, and that L seemed completely unmotivated at that time. There's no reason to call that space L anything, but this is the reason, is that in the continuous time case, we have these spaces L, where L stands for Lebesgue, and then in the discrete time case, you just adopt a version of the notation which is the same. Okay. All right, good. So first, in order to understand what we're doing, first we're going to look at the Riemann integral. Okay. All right. So, the idea here is to carefully, um, or at least present an idea of a careful construction of a definition of the Riemann integral. Okay. All right. So the first thing we'll do is we're going to let f be a real valued function on a compact interval that's bounded. Okay. All right, so I start out with a fairly restrictive case, right? I'm going to talk about functions defined on compact intervals, and I'm going to assume that they're bounded. I'm not going to assume that they're continuous. Okay, and we want to here work with real valued functions just for the time being. The extension to complex valued functions you do just by taking the real and imaginary parts. Okay. Now, so we're going to do a collection of constructions, and I'm going to illustrate those constructions by drawings, because if I just write down all the symbols, I still have to make the drawing. Okay. So I have a bounded function f of x. Okay. All right. And I'm going to draw it like it's positive, but it doesn't need to be. Okay, so it's some bounded function. All right. So I'm just going to kind of, and I want to just sort of emphasize the fact that it's not continuous. Okay. So here's what I do. The first thing I do is I make a partition of the interval AB. And so a partition is going to be a thing P, and what P is just a finite sequence of points between A and B. And so I go x0, right? So A is equal to T0 and B is equal to TK, right? And then I just, string these out somehow. Doesn't really matter for the purposes of the definitions here. Okay, so so I've taken here just for definiteness the case, I guess, of k equals 5. Okay, all right. So let me do that. All right. Okay, now corresponding to a partition P, I'm going to define two functions. And these functions are going to be piecewise constant. And so this means that on each of the intervals of my partition, because my partition divides up the interval AB into 1, 2, 3, 4, 5 partitions, right? Sorry, 5 subintervals. And I'm going to define a function, two functions, each of which are constant on each of these subintervals. Okay, and the way I do that is I define what I call the lower function. So these are piecewise constant, so we call these step functions. Okay, so the lower step function is you take the interval, the first interval from T0 to T1. And on that interval, you take the infimum of the values of F. Okay, so here's where I'm using the fact that F is bounded. Okay, so you take the infimum of the values of F over that interval. And so you get the lower step function. It's going to be take the value there Okay. And then here we take the infimum, which seems to be that point there. So I get something like that. Here I take the infimum, and so unfortunately these are all working out to be, look like they're the same, but it's not necessarily going to be the case. It's just a coincidence. Okay, and then the infimum here will be that, and the infimum here will be that. Okay. All right. So so on each subinterval, I take the infimum of the function, and you can get very easily distracted about which interval do you include the endpoints of the interval in. It doesn't matter. Make a choice. Okay, so that gives me the lower step function, which I call S minus of Fp. Okay. So minus for lower, F for F, and P for P. All right. Okay, then I define the upper step function by doing the same process, but instead I take supremums. Okay, so I take the first interval and I look at the supremum of F over that interval. That'll be like that. Here I look at this interval, like that. This interval is going to be that. So, and then, sorry, this one's going to be like so. Okay, and that function I call S plus of Fp. All right. Okay, and so S minus of Fp is the lower step function. And it's important to notice here that it depends on P, right? It doesn't just depend on F, it depends on P. And then S plus of Fp is going to be the upper step function. Okay, so I choose an F and I choose a P and I do these constructions. All right. All right, so now what I do is I calculate the integrals of these two functions. Okay, so I am defining the integral, so I have to be careful about that. But these are step functions, so it's pretty obvious what the integral is. On each of these subintervals, these functions are constant. Okay, and we may have difficulty computing integrals, but I think we all should agree that the definition of a constant function over some interval is going to be the value of the constant function times the length of the interval. Okay, then define. Okay, so I've committed to the stupid colors, so I'll stick to them. A minus of Fp to be the lower Riemann integral. Okay, and this is going to be the sum, okay, from j equals 1 to k. All right, then it's going to be the value of the lower step function on the interval from tj minus 1 to tj, and I'm going to call that c minus j. Okay, so I'll tell you what that is, times the length of that interval, which is tj minus tj minus 1. Okay, so that is the value of S minus of Fp on Tj minus 1, Tj. And again, I'm not going to fuss about which of the endpoints is included here. You have to make a choice. Doesn't matter what choice you make. The final construction is going to be the same. All right, and then similarly, you have a, oops, I should. So this is going to be the upper Riemann integral. And this is has the same kind of a definition. Okay, except that C plus is the value of S plus on that interval. Okay. All right. So these are just, you can do these constructions for any bounded function on a compact interval. Okay, there's no problem with defining these things for a bounded f. Okay. So now then the idea here is the following, that if you make this partition finer and finer, okay, the idea should be that these two quantities get closer and closer together, and sort of in the limit as the partition becomes finer and finer, they converge and they converge to the same thing, right? So let's formalize that. So a bounded function f on AB is Riemann integrable if for each epsilon positive, there exists a partition P such that A plus of FP minus A minus of FP. All right, so this thing is certainly always going to be non-negative. A plus is always greater than or equal to A minus, but I asked for the difference to be less than epsilon. Okay. Okay, so that's the definition of Riemann integrable. Okay, so we're going to sort of think about this definition a little bit, but let's first say what the Riemann integral is. The Riemann integral is integral A to B f of x dx. Right, that's now I'm defining the integral, so I'm really here defining that notation, right? Okay, so this is going to be the sup or the inf of A plus or A minus. Let's go with sup. Okay, and so again, I could have. So first, let's make a couple of observations. So the first thing is this always is well defined. Okay, and that's because f is bounded, and so this is going to be a bounded collection of numbers, and so the sup is always going to be some finite number. Okay, so you can always do this construction. Now, if f is Riemann integrable, then you could have done the construction with the upper step functions as well. Okay. All right. So it's messy to calculate to prove all of these facts. Okay, but they are true. Okay. All right, but this does rely on f being Riemann integrable, and you can see from the definition why that should work out, right? So the infimum, the supremum of all these guys should equal the infimum of all these guys, just because they can be made to get close together. All right, another fact. Or another way of maybe characterizing the Riemann integral. So to define the Riemann integral, okay, we can define, we're going to take Pj be a partition of AB, such that A plus of Fpj minus A minus of Fpj is less than 1 over j. Okay, now if f is Riemann integrable, I know I can always find such a partition, right? That's the definition. So in this case, the integral can be taken as the limit of the upper Riemann integral and the lower Riemann integral. Right? So it's the limit as j goes to infinity, a plus of f pj, or it's also equal to the limit as j goes to infinity, a minus of f pj. Right? So there's a bunch of different ways of characterizing the Riemann integral of a Riemann integrable function. Okay, you can do that, you can do that, you can do that, you can do that, and then there's other equivalent characterizations as well. Okay. Properties of the Riemann integral. Okay. All right. And so we're going to extend the definition of the Riemann integral, but remember now I'm in this setup here of a bounded function defined on a compact interval. Okay. And the properties here are if f is continuous, it is Riemann integrable. Okay, so that's good. If f and g and so I want to keep in mind here the setup. So let me if f and g are Riemann integrable, then so are f plus g and alpha f, or scalar alpha, and the integral is linear. Okay, and so commutes with addition, and of course also commutes with scalar multiplication. Okay, so there's a couple of properties of the Riemann integral. There's more, but some of which we'll talk about later. But for the purposes of what we're doing right now, what I'm interested in is coming up with an example which illustrates, not to complete satisfaction, but to some satisfaction, the difficulties that arise with the Riemann integral. So we'll look at an example. Well, we'll look at examples, and these examples are going to build. Okay. All right. So let's let t. Sorry. Let me do it this way. Let me let x naught be some point in the interval a b, and let f x naught all right, so this is going to be a very simple function that I've referred to before. So this is a function which is 0 except at a single point, x naught. Okay. All right, so what I said before is that the Riemann integral of this function is 0. So let's make sure that we understand how this follows from the definitions. Okay. All right. Okay, so let's draw the function. So it has the value 1 there and 0 everywhere else. Okay. So let's apply the definition of Riemann integral, and let me first show that it's Riemann integrable, okay, by proving that, and then I'll use one of these definitions of the actual Riemann integral to give the value of the Riemann integral. Okay. All right, to see that f x naught is Riemann integrable, okay, we need to find a partition. Okay, so we need to take an epsilon positive, right? We need to choose our partition so that the difference between the upper Riemann integral and the lower Riemann integral for the function f with that partition is less than epsilon. Okay, and so it's easiest to just draw the partition. A, B, X naught. All right, and all I'm going to do is I'm going to choose a partition with 3 subintervals, and the middle, there's going to be one around X naught, so X naught is going to be in the interior of this partition, in the center if you want, and all I really care about is the width here of this partition is epsilon over 2. Okay, so then I have this is T0, this is T1, this is T2, and this is T3. Okay. All right, so for this partition, A minus of F and P, okay, at some arbitrary point X. Okay, all right, so the lower step function, what this is going to do is it's on each of the 3 intervals of my partition, I take the infimum of the values of F. Okay, so for this partition, obviously the function is identically 0, so the value of the lower step function will be 0, similarly here, but also here, okay, because it has a value 1 at this point and it's 0 everywhere else, so the infimum is 0. Okay, A plus, oh, sorry, I'm writing the step function, not the integral. Okay, and so you can easily see here that this is equal to 0 if X is in T0, T1, or T1, sorry, T2, T3, and it has a value 1 when X is in the middle interval. Okay, because the soup of the values of F in there is going to be 1 because it's equal to 1 there. But these guys, of course, are going to be 0. Okay. Therefore, A plus of Fp minus A minus of F and P. Okay, so the upper Riemann integral is just going to be the integral of this function. Okay, but remember I've chosen the length of this interval to be epsilon over 2. Okay, so this is 1 times epsilon over 2. Okay, and then the lower step function is 0, so the lower Riemann integral will be 0. So this is epsilon over 2, which is less than epsilon. Okay. All right. So therefore, F is sorry, F X naught, and so sorry, there's their X naughts all throughout here. Okay. So Fx naught is Riemann integrable. And, okay, so to calculate the value of the Riemann integral, it suffices, for example, you can do this in all of these different ways, right? Oops, let me not overwrite things. Right, you could choose this or this. You could also choose this or this. And perhaps actually the easiest thing to do is to go with that definition, because we know that that's 0 for every partition P. Okay. And just by the definition of the Riemann integral, integral from A to B f of x dx equal to 0. Okay. All right, so there's a kind of laborious proof of the fact that the integral of a function which takes a non-zero value at a single point is 0. Okay, so if, let's say, f in AB is any finite subset, and if f sub f is this function, okay, so this is going to be the function which is 1 if x is in this finite subset f and 0 otherwise. Okay. Then, f is Riemann integrable. And the integral from A to B, f x dx is equal to 0. Now, why is this? This is just by linearity of the integral. Okay, because f is the sum of x in f x, where f(x) is as above. Okay, right, because so I'm going to choose a point x in f. Then fx is going to be the function which is 1 at x and 0 everywhere else, and so ff is just the sum of all such functions as we run x over f. Okay, so this is a finite sum, and so these properties of the integral apply. Right. Okay, let's give an interesting example, which is not Riemann integrable. Okay, so now let's define f from, let's be concrete now and take the interval 0, 1. Okay, so the f(x) here is going to be the function which is 1 when x is in the rational numbers between 0, 1 and 0 otherwise. All right, so when x is irrational. Okay. All right, so this function is a little bit like the previous ones in the sense that f consists of a function which is 1 on some collection of points and 0 everywhere else. Okay, the the difference here with this function and the previous ones is that in the previous case, the function was 1 at only a finite subset. Here, the set of points in Q, which are in the interval 0, 1, so I made that look like a square bracket, and I didn't want to do that. Okay, the points in Q, which are in the interval 0, 1, that's an accountable but not finite set. Okay. All right. So as we're going to see, there's some problems that come out of that. So let's see how that works. Okay. All right. So here's my function. So 0, 1. Okay. So there's the value 1. Okay. Now to draw the graph of this function takes rather a long time, but it kind of looks like this. Okay. All right. Okay. So my ability to draw straight lines aside, let's check the Riemann integrability of this function. All right. So let's take. So to do that, let's consider an arbitrary partition. Okay. All right, so now let's consider for that partition, let's consider the lower step function and the upper step function. Okay, so so we're going to choose a point x in the interval 0, 1, so there. Okay, and to construct the lower step function, okay, so we take our point x, which is here, okay, and so what we know is there's going to be some interval of the partition which contains x, okay, so there's going to be some little interval around here which has the point, and this is going to be, some interval of the partition, so that point is going to be some tj minus 1, and that's going to be some tj. Okay, now the lower step function is defined to be the inf of all of the values of f between tj and tj minus 1. Well, that's 0. Okay, because no matter how small this interval is, there will always be some rational number, even if x itself is not rational. Sorry, I'm going backwards. There will always be some irrational number in this interval, even if x itself is not irrational. Arbitrarily close to x, there will be some irrational number, and so in particular, in every such interval around x, there will be an irrational number, and so the lower step function will have the value 0. Okay. And by exactly the same reasoning, the upper step function has the value 1. Just replace irrational with rational. Okay, right? So I have x. So even if x is not rational, arbitrarily close to x, there will be some irrational number. And so in particular, in the interval from tj minus 1 to tj, there will be some I think I just said irrational, I meant rational. So there'll be some rational number in this interval, which will force the value of the upper step function to be 1. And this is true for every x. Okay, and so the implication is that a plus of f and p minus a minus of f and p is equal to 1 for every partition P. Okay, and this immediately enforces F not being Riemann integrable. Okay, All right, so there's something, and that's, I know, not that interesting maybe, because who really cares about a stupid function like this? Okay, the more interesting thing about this example is the following thing. Okay, so let's let Qj be an enumeration of the rational numbers between 0 and 1. Okay, so I know that that set is countable. So we talked about the countability of the rationals a long time ago, and so these can be listed in a list indexed by the positive integers. All right, so let me do that in some way. It doesn't matter what way. Okay, for any positive integer k, let's denote gk to be the sum from j equals 1 to k of fx, qj. Okay, and so I'm using the notation that I introduced up here for fx naught, right? So here x naught is equal to qj, right? So fqj is the function which is 1 at qj and 0 everywhere else. So let me just write that down explicitly just to make sure. Like so. Okay. All right, now, this function is Riemann integrable, as we showed in the first of our 3 examples. This is a finite sum of these Riemann integrable functions. So gk is Riemann integrable, and that really is just by the example here, okay, for this function which was non-zero on a finite subset. Okay, so by example 2, gk is Riemann integrable. Okay. Also, the sequence gk of functions converges pointwise to this function f that we're talking about, the function which is 1 on the rationals and 0 on the irrationals. Okay, this is obvious. If you fix any point x in the in the interval 0, 1, okay, then there's 2 possibilities. F is either rational or it's irrational. If it's irrational, then gk evaluated at that point is going to be 0 for every k, and f will also be 0 at that point for every k, and so the sequence consisting entirely of zeros certainly converges to the number 0. Okay, so that's when x is irrational. Now, when x is rational, that means that f is equal to x is equal to qj for some j. Okay, and as long as I choose k to be larger than that value of j, then the value of gk at x will be 1, but the value of f at that x is also 1. And so the sequence, which is eventually consists entirely of 1s, so it might be 0, 0, 0, 0, 0 for some very large but finite number of zeros, and then it all turns 1s. Okay, that will converge to 1, which is the value of f of x when x is rational. Okay, so that gives us pointwise convergence of that sequence. Okay, so thus we have, okay, so we can calculate the integral from 0 to 1 of gk of x dx for every k, and that value is 0. And so certainly the limit as k goes to infinity of this is equal to 0. Okay. Now let's imagine writing the same expression, but now with the limit inside. The integral from 0 to 1 of the limit, and now okay, so now I mean the pointwise limit, right? So you fix an x and then take the limit as k goes to infinity. Okay. Okay, not only does that not equal 0, but this, by my observation here, is equal to the integral from 0 to 1 f of x dx. Okay, and this doesn't exist. Okay, and so therefore this is not true. Okay, and not only is it not true, okay, it's true in a rather violent way. This side is equal to 0, and this side does not exist. Okay, and so this is, in some sense, emblematic of the defect of the Riemann integral, is that you can have a fairly benign pointwise limit, like I have in this case, but it doesn't commute with the integral. The Riemann integral behaves poorly with respect to pointwise limits. Okay. All right, and so we're going to see when we construct the Lebesgue integral, that the Lebesgue integral behaves much more nicely here. And this is really just a defect of the Riemann integral. And really what it comes down to is the fact that you've chosen in the definition of the Riemann integral up here, okay, you've chosen your approximating functions to be too simple. Okay, they're step functions, and step functions are simply not capable of capturing the kind of limiting behavior like you're seeing in an elementary example like this. The limit definition of a function like this, just step functions are just not capable of capturing that. Okay, and in the definition of the Lebesgue integral, you use different kinds of approximating functions, but to get there requires a bit of work. Okay, so next time we'll start talking about the Lebesgue integral, and we'll see that's also a bit of a trick.